Hello students, in the next 10 minutes we are going to discuss an important theorem related to isomorphic vector spaces. Any n-dimensional vector space is isomorphic to Rn. Rn is the vector space of set of all ordered n tuples of real numbers. So any n-dimensional vector space, that is a finite vector space whose dimension is n, is isomorphic to Rn. We have to prove this theorem, that is any vector space is isomorphic to Rn. Let phi be a vector space with the dimension of phi is equal to n. For that we have taken a vector space phi whose dimension is n. Then let phi1, phi2, phi be any ordered basis of phi. Then we have to define an isomorphism between this vector space phi and Rn. Let phi be a vector space, then there exists a unique scalars alpha 1, alpha 2, alpha n belongs to R, such that phi is equal to alpha 1 v1 plus alpha 2 v2 plus and so on alpha n vn. Because phi is a vector space and v1, v2, vn are basis vectors of phi, therefore any vector phi belongs to phi can be expressed uniquely as a linear combination of these vectors. So there exist unique scalars alpha 1, alpha 2, alpha n belongs to R, such that phi is equal to alpha 1 v1 plus alpha 2 v2 plus and so on alpha n vn. Now we are going to define a linear transformation. See here how the linear transformation is defined. Define a linear transformation T from phi to Rn by T of phi is equal to T of phi, means now phi is this linear combination of phi1, phi2, phi So T of alpha 1 v1 plus alpha 2 v2 and so on alpha n vn is equal to alpha 1 comma alpha 2 and so on alpha n. This is the ordered n tuples of real numbers. These scalars are real numbers. So this is the ordered n tuples of real number. So this alpha 1, alpha 2, alpha n must this belongs to Rn. Okay. Then we have defined this linear transformation T from phi to Rn by this way. So for all phi belongs to phi, we have to prove that T is well defined. As the scalars alpha 1, alpha 2, alpha n are uniquely determined, the T is well defined. Means what? If this is a vector phi and the v can be written as like this, then this is unique. So this is a well-defined transformation. Now we are going to prove that this transformation is linear. This is a transformation, this is a map, this is a well-defined map. This we have to define, we are going to prove that this transformation T is linear. So let phi dash is equal to alpha 1 dash v1 plus alpha 2 dash v2 plus and so on alpha n dash vn, where these vectors alpha I dash belongs to R for all 1 is less than I is less than or equal to n. Now consider T of phi plus v dash. T of phi plus v dash is equal to phi plus v dash is nothing but alpha 1 plus alpha 1 dash into phi1 plus alpha 2 plus alpha 2 dash into phi2 and so on alpha n plus alpha n dash into phi n. So T of this vector is equal to the scalars we have ordered n tuple. So alpha 1 plus alpha 1 dash, alpha 2 plus alpha 2 dash and so on alpha n plus alpha n dash. So this can be written as sum of two ordered n tuples. Here in the first component alpha 1 plus alpha 1 dash, alpha 2 plus alpha 2 dash and so on alpha n plus alpha n dash. But already we have defined that alpha 1, alpha 2, alpha n is T of phi, and similarly this is T of phi dash, and this holds for all phi comma phi dash belongs to phi. So first condition for linear transformation is satisfied. Second condition, let alpha belongs to R, T of alpha phi is equal to T of alpha alpha on phi1, alpha into alpha 2 phi 2 plus and so on alpha into alpha and phi n. This is by just the definition of scalar multiplication. This is equal to alpha alpha 1 by definition of a T, alpha alpha 1 first tuple, second tuple alpha alpha 2 and so on alpha alpha n. First component, second component, last component, nth component is alpha alpha n. So this is equal to alpha into alpha 1 comma alpha 2 and so on alpha n. This is equal to alpha into T of phi, because this ordered n tuple alpha 1 alpha 2 alpha n is T of phi. So T of alpha phi is equal to alpha into Tv for all alpha belongs to R and phi belongs to it. Therefore T is a linear transformation. Next we have to show that T is a isomorphism. For that we have to show that T is 1 1. Let T of phi is equal to T of phi dash, phi comma phi dash belongs to phi. We have to show that T is 1 1. For that we have considered this T of phi equal to T of phi dash. If image of two vectors are same, then that vectors must be same. Then T is a 1 1. That is distinct elements of distinct images. That is, if the images are same, then the corresponding vectors must be same. So T of phi is equal to T of phi dash implies alpha 1 comma alpha 2 and so on alpha n, because this is the value of T of phi. T of phi dash is equal to alpha 1 dash comma alpha 2 dash and so on alpha n dash. So this implies that by equality of two n tuples, alpha 1 is equal to alpha 1 dash, alpha 2 equal to alpha 2 dash and so on alpha n is equal to alpha n dash. This implies that alpha 1 phi1 plus alpha 2 phi 2 plus and so on alpha n phi n. So here alpha 1 is alpha 1 dash, alpha 2 is alpha 2 dash. So this is equal to alpha 1 dash phi1 plus alpha 2 dash phi 2 plus and so on alpha n dash phi n. This is nothing but phi and this is nothing but phi dash. So this implies that phi equal to phi dash. Therefore T is a 1 1 map. Now we are going to show that this T is a onto map. For that, let beta is equal to beta 1, beta 2, beta n be any ordered n tuple in a vector space Rn. That is, be any factor. Then let phi beta is equal to beta 1 phi1 plus beta 2 phi 2 plus and so on beta n phi n belongs to phi, because phi is a vector space and phi is closed with respect to scalar multiplication. Therefore this must be belongs to phi, and phi1 phi2 phi n are basis vectors. So this linear combination must belongs to phi. See here, this linear combination belongs to phi, and moreover T of phi beta is equal to T of beta 1 phi1 plus beta 2 phi 2 plus and so on beta n phi n is equal to beta 1 comma beta 2 and so on beta n by definition of T. Just we have defined the T. This is equal to beta. Beta is beta 1 ordered n tuple beta 1, beta 2 and so on beta n. Therefore T is on 2. Why T is on 2? Because for any vector beta is equal to beta 1, beta 2, beta n belongs to Rn. There exists a vector v beta is equal to beta 1 1 plus beta 2 phi 2 plus and so on beta n phi n, such that T phi beta is equal to beta. Therefore T is on 2, and thus from 1, 2, 3 and 4 T is a linear isomorphism. Therefore this vector phi is isomorphic to Rn. Hope you understand, student. This is a very simple proof. Hence the proof. Thank you, students.